What if the modern world isn't as original as we think? Picture this thousands of years ago. Ancient civilizations scribbling symbols, carving artifacts, and telling stories that eerily resemble the smartphones, aircraft, and medical miracles we take for granted today. It's as if they glimpsed the future long before it arrived. How could cultures separated by centuries, even millennia, predict technologies that wouldn't exist for ages? The answer lies in a series of bewildering artifacts, texts, and myths that suggest our ancestors weren't just primitive societies, but perhaps visionaries who caught fragments of a future they could hardly comprehend. This isn't science fiction, it's history whispering secrets across time. From the precision of Egyptian hieroglyphs hinting at electrical grids to the intricate mechanics of the Antikythera device, a 2,000-year-old analog computer, the evidence is staggering. These weren't lucky guesses, they were meticulous observations, perhaps even lost knowledge, pointing to a startling truth. Ancient minds may have grasped concepts we consider modern breakthroughs. Imagine holding a clay tablet that describes something like a smartphone or reading a myth that mirrors space travel. The line between legend and reality blurs, leaving us to wonder, did ancient cultures have access to wisdom we've only rediscovered? That's the journey we're embarking on today. We'll unravel 25 jaw-dropping examples where the past eerily foreshadowed the present. From Greek fire that behaved like napalm to Sanskrit texts detailing what sounds like genetic engineering, these aren't mere coincidences. They're puzzles waiting to be solved, so settle in because by the end of this exploration, you might never look at history the same way again. The past isn't just behind us. In ways we're only beginning to understand, it might have been ahead of us all along. The first jaw-dropping example takes us beneath the waves off the coast of Greece in the year 1901. Divers searching for sunken treasure stumbled upon something far more valuable, a corroded bronze artifact no bigger than a shoebox, encrusted with centuries of sea growth. At first glance, it seemed unremarkable, but when archaeologists painstakingly cleaned it, they uncovered gears. Dozens of interlocking bronze gears with precision teeth, arranged in ways that shouldn't have existed for another 1,000 years. This was the Antikythera Mechanism, and it would shatter everything we thought we knew about ancient technology. Dating back to around 100 BC, this intricate device wasn't just ahead of its time, it was light years ahead. Imagine a world without electricity, where philosophers debated the nature of the cosmos without telescopes or calculators. Yet here was a machine that could predict the movements of the sun, moon, and planets with staggering accuracy. It could forecast eclipses, track the cycles of the Olympics, and even account for irregularities in the moon's orbit, a feat that wouldn't be replicated until the mechanical clocks of 14th century Europe. The genius of the Antikythera Mechanism lies in its complexity. Modern X-ray scans revealed miniature gear trains, differential systems, and even a pin and slot mechanism to model celestial motion. To put it plainly, this wasn't just a calendar or a simple astrolabe. It was a fully functional analog computer, a device so advanced that scholars initially dismissed it as impossible until the evidence became undeniable. What's truly mind-bending is how closely its design mirrors early modern calculating machines. In the 17th century, inventors like Blaise Pascal and Gottfried Leibniz built mechanical calculators to perform basic arithmetic. Yet here was the ancient world crafting a device that didn't just add numbers, it mapped the heavens. The implications are staggering. Was this a one-of-a-kind invention or a glimpse into a lost tradition of ancient engineering? Some theorists suggest it might have been based on knowledge passed down from even earlier civilizations like the Babylonians, whose astronomical records were shockingly precise. The Antikythera Mechanism forces us to rethink history's timeline. If the Greeks could build something this sophisticated, what else might they or other ancient cultures have known? It's a humbling reminder that brilliance isn't confined to the modern era. Sometimes the past holds technologies so advanced we're only just catching up. To truly grasp the genius of the Antikythera mechanism, we need to peer inside its corroded bronze shell. Picture 37 meticulously interlocking gears, some with teeth so fine they resemble the workings of a modern wristwatch. These weren't crude notches hacked into metal. They were precision cut, designed to mesh perfectly as they turned, transferring motion from one gear to another with astonishing accuracy. The largest gear at the heart of the device boasted 223 teeth, a number that wasn't arbitrary. It matched the 19-year metonic cycle used by ancient astronomers to predict lunar phases and eclipses. What makes this ancient computer so revolutionary is how it mirrored celestial mechanics. One gear represented the sun's movement, another the moon's elliptical orbit, and a third even accounted for the moon's subtle wobble, a phenomenon called nodal precession. This wasn't just tracking time, it was modeling the cosmos in miniature using differential gearing, a technique thought to have been invented in the 16th century for steam engines. The mechanism's front face likely displayed concentric rings showing planetary positions, while dials on the back predicted eclipses and even marked the dates of the Olympic Games. Modern reconstructions reveal the device's true brilliance. Using high-resolution X-ray tomography, scientists deciphered inscriptions hidden beneath millennia of corrosion instructions that functioned like an ancient user manual. One fragment even described how to adjust the mechanism for leap years. The craftsmanship was so advanced that early researchers assumed it must have fallen into the sea from a passing time traveler's ship. Why did this technology vanish for over 1,000 years? The answer might lie in the fragility of knowledge. The Antikythera mechanism wasn't mass-produced. It was likely the work of a single workshop, perhaps inspired by the legendary inventions of Archimedes. When Rome conquered Greece and later when libraries like Alexandria burned, such specialized engineering may have been lost, along with the minds who understood it. The eerie part, similar devices appear in historical records but haven't survived. Cicero wrote of a bronze sphere built by Archimedes that modeled planetary motion. The Byzantines later described celestial globes so precise they could predict eclipses centuries in advance. The Antikythera mechanism wasn't an anomaly. It was a glimpse into a shadow tradition of ancient genius, one that makes us wonder how many other marvels turned to dust while we assumed the past was simpler than it really was. Traveling from the depths of the Aegean to the sands of Mesopotamia, our next ancient mystery comes in the form of unassuming clay pots, objects so ordinary at first glance that archaeologists initially catalogued them as simple storage jars. That is, until someone noticed the copper cylinders inside, the iron rods carefully suspended within them, and the traces of an acidic residue coating the interiors. These were the Baghdad Batteries, and they've sparked one of history's most electrifying debates. Did the Parthians 2,000 years ago harness electricity centuries before Volta invented his famous pile? Discovered in 1936 near the village of Kayat Rabawa outside modern Baghdad, these artifacts date back to between 250 BC and 250 CE. Each battery consisted of a terracotta jar roughly the size of a fist, sealed with asphalt and housing a rolled copper sheet surrounding an iron rod. When filled with an acidic liquid like vinegar or grape juice, experiments showed these jars could produce up to 2 volts of electricity, enough to generate a faint current. The question isn't just whether these devices worked, but why they existed. One theory suggests they were used for electroplating, coating objects like jewelry with thin layers of gold or silver. Ancient Mesopotamians were master metalworkers, and artifacts from the region show gilding techniques that could have been achieved through electrochemical processes. Imagine a craftsman dipping a silver ring into a solution, connecting it to one of these jars, and watching as a shimmering layer of gold gradually bonded to its surface. It's a tantalizing possibility, especially when you consider that similar basic batteries were used for electroplating in 19th century Europe, but not everyone's convinced. Skeptics argue there's no direct evidence linking the jars to metalworking. No electroplated artifacts from the period have been definitively tied to the batteries, and no wires or electrodes have been found alongside them. Alternative explanations propose they stored sacred scrolls or were used in religious rituals, perhaps to deliver mild shocks during ceremonies, creating a divine tingle to all worshippers. One particularly creative hypothesis even suggests they powered early versions of electric fish traps, a practice documented in later Arabic texts. What makes the Baghdad batteries so fascinating is how perfectly they mirror the principles of modern voltaic cells. The basic components are identical: two dissimilar metals, copper and iron, immersed in an electrolyte, the acidic liquid, separated by a barrier, the asphalt stopper, to prevent short-circuiting. It's the same chemical reaction that powers your smartphone today, just scaled down to ancient proportions. Could this have been accidental? Unlikely. The design is too deliberate, the materials too carefully chosen. Even if the Parthians didn't fully grasp the science, they might have stumbled upon a practical application through trial and error, much like how ancient brewers fermented beer without understanding microbiology. The real shocker: if these were indeed batteries, they predate the Western world's discovery of electricity by nearly 2 millennia. Yet here's the twist: unlike the Antikythera Mechanism, which was a lone survivor, multiple Baghdad batteries have been found. This wasn't a one-off experiment. It was a technology replicated across generations, hinting at a broader, now lost tradition of experimentation. Whether for plating metals, startling temple visitors, or some other purpose we've yet to uncover, these jars force us to reconsider history's timeline once more. Sometimes the spark of innovation strikes far earlier than we expect, and the past hums with currents we're only beginning to measure. While the Baghdad batteries sparked debates about ancient electricity, another invention from the classical world hints at an even more staggering technological leap, one that could have rewritten the course of industrial history. In the 1st century CE, inside the bustling workshops of Alexandria, an inventor named Heron built a device that harnessed the raw power of steam. Known as the eclipse, this brass sphere with protruding tubes wasn't just a curious gadget. It was the world's first recorded steam engine, spinning with violent force when heated, a principle that wouldn't be widely used again until the 18th century. Heron's design was deceptively simple. Picture a hollow metal ball mounted on an axle, with two bent nozzles projecting from opposite sides like outstretched arms. When the base was filled with water and placed over a fire, steam rushed through the tubes, escaping at angles that sent the sphere whirling at dizzying speeds. Modern recreations show it could reach up to 1,500 revolutions per minute, a mesmerizing display of force that must have seemed like magic to ancient observers. What's baffling isn't just the eclipse's existence, but how it was used. Unlike the steam engines that later powered factories and locomotives, Heron's invention wasn't employed for labor or transportation. Instead, ancient texts describe it as a temple wonder, a device to impress worshippers by making statues seem animated or to power small mechanical plays. Imagine walking into an Egyptian sanctuary 2,000 years ago and witnessing doors that appeared to open on their own, powered by hidden steam mechanisms. To the people of that time, it wasn't technology, it was the handiwork of the gods. This raises a haunting question. If the principles of steam power were understood so early, why did it take 1,700 more years for humanity to harness it for industry? Some scholars argue the eclipse was seen as a toy because ancient societies lacked the need for mass production. Slavery and abundant manual labor made labor-saving inventions less urgent. Others point to materials. The metallurgy needed to build pressure-resistant boilers didn't exist yet, limiting practical applications. But the most compelling theory might be cultural. The ancient world prized knowledge for its own sake, not for utility. Heron himself wrote extensively about pneumatics and mechanics, yet his work was shelved alongside philosophical treatises rather than blueprints for workshops. When Rome fell and Alexandria's libraries burned, these ideas faded into obscurity, waiting to be rediscovered in an age that valued engines over entertainment. The tragedy of the Eolipile isn't just its forgotten potential. It's a reminder that innovation depends as much on circumstance as genius. Steam power existed millennia before the Industrial Revolution, but without the right economic pressures, societal needs, and technological infrastructure, even the most groundbreaking invention can remain a curiosity rather than a catalyst. Heron's spinning sphere wasn't ahead of its time, it was trapped by it. Heron of Alexandria didn't just tinker with steam, he engineered miracles. Among his most astonishing creations was a system of temple doors that seemed to open by divine will. Picture this: worshippers gathered at an Egyptian shrine in the 1st century, watching as flames flickered atop an altar. As heat from the fire expanded air in hidden brass pipes, pressure built until, without a single touch, massive wooden doors slowly swung outward, as if the gods themselves were granting entry. This wasn't sorcery, it was pneumatics mastered 2,000 years before modern hydraulics. The mechanism relied on principles we still use today. Heron's design connected the altar to a series of tubes filled with water and air. When priests lit the sacrificial fire, the expanding warm air pushed water through a siphon into weighted containers. As these containers grew heavier, they pulled ropes tied to the door's pivots, creating seamless movement. The effect was so flawless that some historians believe these doors inspired myths of temples that came alive for chosen devotees. What's striking is how closely this mirrors contemporary automation. Modern motion sensors may use infrared beams instead of fire, but the underlying idea remains identical: detecting an invisible trigger, heat, or movement to activate machinery. Heron even included timing mechanisms, vessels that emptied at a controlled rate, ensuring doors stayed open just long enough for rituals before gracefully closing. It's the same logic behind today's supermarket entrances, where delayed shutoff prevents accidents. Yet the real brilliance lies in the psychology. Heron understood spectacle. His doors didn't just function, they performed. The delay between ignition and movement made the event feel supernatural, heightening the drama of religious ceremonies. Compare that to Disney's Imagineers, who use similar tricks with hydraulic animatronics to suspend disbelief. Both ancient and modern engineers realized technology's power isn't just in utility, but in wonder. Why didn't this spark an industrial revolution? The same constraints that limited the Eolipile applied here. Without standardized metal casting or rubber seals, maintaining large pneumatic systems was impractical. Temples could afford these marvels as one-off installations, but scaling them for everyday use was impossible with classical materials. Heron's inventions weren't failures. They were trapped in an era that couldn't fully exploit them, waiting for futures where pressure valves and sensors would turn theatrical magic into mundane convenience. The haunting beauty of these doors isn't just their ingenuity. It's the realization that automatic entrances, now so ordinary we barely notice them, were once dreams forged in fire and bronze. Every time you walk through a motion-activated portal, you're stepping into a vision Heron brought to life millennia ago, proving that the past never really vanishes. It just waits for us to rediscover it. While modern concrete crumbles after decades, Roman harbors have withstood 2,000 years of pounding waves, not despite the sea's corrosive power, but because of it. This paradox lies at the heart of one of antiquity's most enduring engineering secrets, a self-healing concrete so advanced that today's scientists are only just decoding its genius. Dive into the waters near Pozzuoli, Italy, and you'll find the proof. Submerged breakwaters built during Augustus's reign still stand intact, their surfaces barely weathered, while modern counterparts nearby deteriorate after mere years. The difference: ancient engineers didn't fight seawater, they weaponized it. At first glance, Roman concrete seems primitive. Unlike our smooth, uniform blends, it contained jagged chunks of volcanic rock and a curious ingredient called quicklime, a highly reactive form of calcium oxide. For centuries, historians assumed these inclusions were flaws or signs of inferior mixing, but recent studies using microscopic imaging revealed the truth. Those imperfections were the concrete's resurrection mechanism. When seawater seeped into cracks, it reacted with the lime clasts, triggering a chemical cascade that formed new mineral growth. These crystals, often fibrous minerals like stretlingite, stitched fractures back together, turning weaknesses into reinforced seams. It's as if the concrete possessed a biological immune system, healing itself the moment damage occurred. Modern materials scientists are racing to replicate this process. Today's self-healing concretes often rely on embedded bacteria or microcapsules of glue-like compounds, complex solutions that pale beside the Romans' elegant chemistry. Their formula needed no artificial additives. Instead, it leveraged natural volcanic ash, pozzolana, and salt water's transformative power, creating a sustainable cycle of decay and regeneration. The irony is staggering. While we pump billions into repairing corroded bridges and eroding seawalls, the ancient world built infrastructure designed to last millennia with materials dug straight from the earth. The secret weapon: hot mixing. Roman builders didn't pre-dissolve lime as we do. They tossed chunks of quicklime directly into the mixture, creating unstable pockets that remained chemically dormant until activated by moisture. Think of it like a repair kit buried inside the concrete, waiting for the right moment to deploy. When seawater penetrated, it triggered a delayed reaction, forming calcium-rich solutions that flowed into cracks and recrystallized, a process mimicking how bones heal. Modern X-rays of ancient harbor walls show these repair minerals layered like geological tree rings, documenting centuries of microfractures and their spontaneous fixes. What's humbling isn't just the Romans' technical prowess, but their long-term thinking. They engineered for permanence in an era without pressure to cut costs or speed construction. Compare that to today's concrete, optimized for quick pouring and early strength at the expense of longevity. The Pantheon's dome, still the world's largest unreinforced concrete structure after 2 millennia, laughs in the face of modern parking garages that crumble in 30 years. Perhaps the true lesson isn't just about chemistry, but philosophy. The ancients built as if their creations needed to outlast empires, and against all odds, some still do. Now, laboratories from MIT to Berkeley are cracking the code. By reintroducing Roman-style lime clasts into modern mixes, teams have created prototypes that repair hairline cracks within weeks of saltwater exposure. The implications are monumental. Imagine seawalls that grow stronger with each storm, or nuclear waste containment that self-seals for centuries. For once, cutting-edge innovation means looking backward, to an era when concrete wasn't just poured, but engineered to endure time itself. The Romans may not have understood atomic structures or nanotechnology, but their concrete proves one timeless truth. Sometimes the most advanced solutions are hiding in plain sight, waiting 2,000 years for us to catch up. In the year 132 CE, while most of the world still blamed earthquakes on angry gods or mythical creatures stirring beneath the earth, a brilliant Chinese inventor named Zhang Heng unveiled a device that would challenge superstition with science. His seismoscope, a towering bronze urn adorned with 8 intricately carved dragon heads, wasn't just decorative. It was a working earthquake detector so precise it could pinpoint the direction of tremors hundreds of miles away, centuries before modern seismographs even existed. The design was as elegant as it was ingenious. Each dragon cradled a bronze ball in its jaws, poised above 8 corresponding toads with gaping mouths. When an earthquake's vibrations traveled through the ground, an internal pendulum mechanism would tilt toward the tremor's origin. This motion triggered a hidden lever, releasing just one ball from its dragon's mouth into the waiting toad below with a resonant clang. The direction of the fallen ball revealed the quake's epicenter, a system so reliable that historical records claim it once detected a quake 400 miles away that no one in the capital had even felt. What's truly astonishing is how closely Zhang Heng's principles mirror modern seismology. Inside that ornate urn lay a simple yet effective inertial mass, likely a suspended pendulum or weighted column, that stayed relatively still while the Earth moved around it. This differential motion activated the release mechanism, not unlike how today's seismometers use pendulums or springs to detect ground displacement. The real stroke of genius was the directional specificity. Modern networks require multiple sensors to triangulate quakes, but Zhang's device accomplished this with a single instrument, using precise counterweights to ensure only the dragon aligned with the tremor's path would release its ball. Recreations have proven its accuracy. In 2005, scientists from the Chinese Academy of Sciences built a replica using historical descriptions. When tested against recorded earthquake waves, it correctly identified directions every time, proof that this wasn't just ceremonial theater but calibrated engineering. The device even accounted for false triggers. Its internal dampening system prevented balls from dropping during minor vibrations like passing carts or crowds, focusing only on sustained seismic waves. Zhang Heng's seismoscope hints at a profound understanding of earth sciences lost to time. Ancient Chinese texts describe earthquakes as shifts in Chi energy along underground channels, an abstract concept that unintentionally mirrors modern plate tectonics theory. While they didn't grasp continental drift, their observations of tremor patterns and aftershocks suggest systematic study. Some scholars argue the seismoscope's design implies knowledge of P waves, the fast-moving primary seismic waves that arrive first during quakes. By tuning the pendulum's sensitivity, Zhang might have been isolating these precursor vibrations to provide early warning. The tragedy is that only descriptions survive. Like so many ancient marvels, the original seismoscope vanished, possibly melted down for its bronze during wars or dynasty changes. Later Chinese inventors tried recreating it, but none matched Zhang's precision. It wasn't until 1880 that the first modern seismograph emerged in Japan, over 1700 years after that bronze urn first trembled in response to distant upheavals. Perhaps the most humbling thought is this: for all our digital sensors and satellite networks, Zhang Heng's core insight remains unchanged. Earthquakes speak through motion, and sometimes the simplest mechanical translation, a swinging weight, a lever, a falling ball, can decipher nature's whispers more eloquently than the most advanced electronics. In an age without microscopes or wave theory, that urn didn't just detect quakes. It whispered back to the earth in a language we're still learning to speak fluently. Few ancient documents hold the mystique or the scientific precision of the Dresden Codex. This fragile Mayan bark paper book, surviving floods and European book burnings, contains astronomical insights so advanced that modern researchers initially doubted its authenticity. Nestled among its 74 pages is something extraordinary: eclipse tables predicting lunar and solar eclipses with accuracy that rivals NASA supercomputers. Not only did the Maya track these celestial events, they calculated them centuries in advance using a calendar system more precise than anything Europe had until the Renaissance. The brilliance lies in the math. Unlike Western calendars that drifted out of sync with solar cycles, the Mayan long count calendar measured time in meticulously coordinated cycles. Their famed calendar round wove together two separate counts, a 260-day sacred cycle and a 365-day solar year synchronizing every 52 years. But for eclipses, they drilled deeper. The Dresden Codex's eclipse table spans 11,960 days, about 33 years, marking intervals where eclipses were likely. This wasn't guesswork. The Maya recognized the Saros cycle, a repeating 18-year, 11-day pattern where eclipses recur under similar geometries. Modern astronomy confirms their calculations aligned with actual eclipse dates with over 80% accuracy. How did they achieve this without telescopes or written records of Greek astronomy? The answer lies in generations of naked eye observation. Mayan priests meticulously logged celestial events on stelae and codices, noting patterns invisible to casual observers. Their numbering system, using bars and dots with a placeholder 0, a concept Europe wouldn't adopt for centuries, enabled complex calculations. The Dresden Codex even accounts for the moon's subtle orbital wobble by adjusting predictions, proving they understood celestial mechanics weren't perfectly periodic. Compare this to contemporary medieval Europe, where eclipses were seen as divine omens. While monks scribbled about dragons swallowing the sun, Mayan astronomers treated eclipses as calculable phenomena. Their tables didn't just predict dates, they accounted for visibility, noting when eclipses would be obscured by horizon or weather. Some scholars argue the Codex hints at an even grander ambition, a unified theory linking planetary movements, Venus cycles, and eclipses into a single cosmic clockwork. The tragedy, most of their knowledge was destroyed. Spanish bishops burned thousands of codices as pagan lies, leaving only 4 surviving Maya books. The Dresden Codex barely escaped rescued from a Vienna library's floodwaters in the 19th century. Today, digital scans reveal hidden corrections where scribes fine-tuned their predictions, showing science in action. What's unsettling is how close we came to losing this. Had one more hurricane or zealous missionary intervened, we might never have known that ancient astronomers, working without lenses or metal tools, matched precision we assumed was modern. The next time you check a weather app for sunset times, remember, the Maya did it first, carving their celestial insights into bark paper while the rest of the world still feared the sky's shadows. Syracuse, 214 BC, a besieged city facing the might of Rome's navy, with one aging genius standing between them and annihilation. The legend goes like this. As Roman galleys closed in, Archimedes unveiled his ultimate weapon, an array of polished bronze mirrors, their surfaces angled to concentrate sunlight into a searing beam. One by one, the ships burst into flames, their sails and wooden hulls reduced to ash by what history would call the Death Ray. For centuries, this tale straddled the line between plausible innovation and fantastical myth. But what if the world's first directed energy weapon wasn't just a story? Modern attempts to recreate the Death Ray have fueled fierce debate. In 2005, a team from MIT took on the challenge, arranging 127 mirrored panels to focus sunlight onto a mock Roman ship 80 meters away. Within minutes, flames erupted, proving the concept worked under ideal conditions. But critics pounced. The MIT test required stationary targets, perfectly clear skies, and a crew carefully adjusting each mirror, luxuries Archimedes wouldn't have had during battle. Skeptics argue that Syracuse's harbor conditions, shifting ships, ocean spray dulling reflectivity, and the time needed to ignite would make the feat implausible. The tension between legend and reality grows thicker when examining ancient sources. The earliest accounts, written centuries after Archimedes' death by authors like Lucian and Galen, describe the mirrors in vague terms. Notably, the historian Polybius, who documented the siege in detail, never mentions the Death Ray, focusing instead on Archimedes' more conventional war machines, massive cranes that capsized ships and catapults raining down stones. This omission raises questions. Was the mirror weapon a later embellishment, or did Polybius omit it because it seemed too outlandish for his readers to believe? Archaeological clues add another layer. Fragments of highly reflective bronze plates were found near Syracuse's ancient walls, materials that could have served as mirrors. Ancient Greek texts also reference burning glasses used to start fires, suggesting the basic principle was known. Archimedes, a pioneer of optics who studied light refraction, certainly possessed the theoretical knowledge to design such a system. The real mystery isn't whether it was possible, but whether it was practical amid the chaos of war. Perhaps the truth lies in compromise. Instead of a single death ray, smaller-scale mirrors might have been used defensively, blinding rowers, scorching rigging, or creating signal flares to coordinate resistance. Recent experiments show that even scattered light could disorient crews, making ships vulnerable to traditional attacks. This aligns with Archimedes' reputation for psychological warfare. His mechanical claws that lifted ships from the water weren't just deadly, they demoralized enemies with their terrifying ingenuity. What makes this legend endure isn't just the question of historical accuracy. It's the haunting idea that a mind from the 3rd century BC could conceive of energy weapons, a concept humanity wouldn't fully realize until lasers emerged in the 1960s. Whether fact or fable, the death ray symbolizes a recurring theme: the ancient world's capacity for ideas so advanced they blur the line between inventor and prophet. Archimedes may have been sketching the principles of focused light while his contemporaries still saw the sun as a god's chariot. That gap between imagination and execution, between what he envisioned and what his era could realistically deploy, might be the most telling clue of all. The mirrors themselves, if they existed, are long lost, melted down for coins or armor. But their legacy lingers in modern directed energy research, where scientists cite Archimedes as an unexpected forebear. Next time you use a magnifying glass to burn a leaf, remember, you're playing with a fragment of a 2,000-year-old weapon that may have once held empires at bay. Some inventions are too revolutionary for their time, not because they fail, but because the world isn't ready to wield them. Deep within the Temple of Hathor at Dendera, a series of enigmatic carvings crawl up the walls, strange objects resembling oversized light bulbs with snaking cables, each bulb cradling what looks like a glowing filament inside a glass enclosure. To modern eyes, the resemblance is uncanny. Could these 2,000-year-old reliefs actually depict ancient electric lighting, a technology supposedly invented millennia later? The so-called Dendera light has become one of Egyptology's most heated debates, pitting unconventional theorists against mainstream scholars in a clash of interpretations that reveals just how slippery ancient symbolism can be. The controversial images appear in the temple's subterranean crypts, a space reserved for sacred rituals. Each bulb consists of an elongated, teardrop-shaped pod supported by a pillar-like base with a wavy line, interpreted by some as an electrical cable connecting it to a box marked with hieroglyphs. Inside the pod, a serpent extends along its axis, surrounded by what could be read as rays or filaments. At the pod's base, a figure often identified as the god Harsomptus appears to hold the setup. To proponents of the ancient technology theory, this screams electric lamp, the pod as a bulb, the serpent as a filament, the cable as wiring, and the box as a power source. Some even suggest the Egyptians used primitive batteries like the Baghdad artifacts to illuminate tombs, citing the absence of soot marks in certain underground chambers as evidence. Mainstream Egyptologists, however, dismantle this reading piece by piece. The bulbs, they argue, are stylized depictions of lotus flowers, a sacred symbol of creation in Egyptian cosmology. The filament is more likely the Djed pillar representing stability, entwined with the snake goddess Wadjet, a motif tied to royal power and rebirth. The wavy lines, not cables at all, but symbolic representations of the primordial waters from which life emerged. As for the power box, it's a shrine holding the divine birth scene of Harsomptus, a solar deity associated with dawn. Context matters. These carvings share walls with other ritual imagery, all part of an intricate narrative about the cyclical rebirth of the sun, God, not an electrical engineering manual. One of the most compelling counterarguments lies in the Egyptians' own words. Accompanying hieroglyphs describe the scenes in spiritual terms, referencing the sun's journey through the night and the serpent of light. There's no mention of artificial illumination or technology. Even the absence of soot in some tombs has mundane explanations. Ventilated oil lamps or reflective surfaces could achieve clean lighting without electricity. And if the Egyptians had light bulbs, why is there zero physical evidence, no glass shards, no wiring remnants, just these cryptic carvings? Yet the debate persists because it taps into a deeper tension: how we project modern frameworks onto ancient minds. To us, a coiled serpent inside an elongated vessel inevitably suggests a filament in a vacuum tube. But to the Egyptians, serpents symbolized chaos and order, death and regeneration, layers of meaning lost when we force their iconography into our technological lens. The Dendra carvings aren't a puzzle to solve but a mirror, reflecting our own fascination with the idea that advanced knowledge might have been lost to time. Perhaps the most fascinating twist: both interpretations might hold slivers of truth. While the imagery is almost certainly symbolic, some researchers speculate it encodes an understanding of electrical phenomena. The Egyptians knew of electric fish like the Nile catfish, which delivers painful shocks. Could temple priests have harnessed similar natural forces for ritual effects, statues that spoke via hidden tubes or chambers illuminated by bioluminescent algae? The line between sacred metaphor and applied science might have been blurrier than we assume. What makes Dendra unforgettable isn't whether the carvings show light bulbs, but how they force us to grapple with the limits of our imagination. For all our modern arrogance, we still struggle to decipher whether an ancient artist carved a flower, a lamp, or something far stranger that no longer has a name. The past refuses to sit still. It flickers like a bulb switching on in a dark room, casting shadows that shift with every angle of interpretation. Buried within ancient Sanskrit text lie descriptions so precise, so mechanically detailed, they read like pages ripped from a modern aerospace manual. The Vimana's mythical flying chariots said to traverse the skies in Hindu epics like the Mahabharata aren't just fantastical legends. They're meticulously documented vehicles with specifications that include mercury vortex engines, layered protective hulls, and even guidance systems. One passage from the Vaimanika Shastra, a cryptic 4th century BC text, describes a craft propelled by quicksilver engines that generate lift through rotating magnetic fields, a concept disturbingly close to modern ion thrusters and electromagnetic propulsion experiments. The parallels are impossible to ignore. These texts speak of Vimanas being constructed from heat-resistant metals, their interiors cooled by liquid mercury systems. Some accounts even mention energy crystals used for navigation, a detail that echoes contemporary research into laser gyroscopes. When the ancient text claims certain crafts could rend the sky with thunderous noise or hover silently like modern drones, it's hard not to draw connections to today's debates around UFO propulsion theories. Even the triangular-shaped Vimanas described in the Samaranganasatradhara match eerily with modern reports of unidentified aerial phenomena. Critics argue these texts are purely allegorical poetic metaphors for spiritual ascension. But the engineering specifics complicate that dismissal. The Vaimanika Shastra details procedures for takeoff, cruising altitudes, and even emergency landings. One passage warns pilots to avoid bird strike incidents, while another describes using parabolic mirrors to shield against solar radiation. These aren't vague mythic tropes, they're operational concerns that only make sense for actual flight technology. Modern scientists have taken these descriptions seriously enough to test them. In 2001, a team at the Indian Institute of Science attempted to recreate a mercury-based propulsion system based on the text. While inconclusive, their experiments confirmed mercury exposed to high-voltage currents can produce thrust, a principle NASA explored in its now-abandoned Project Orion. The ancient texts also reference vortex propulsion, where rotating mercury creates electromagnetic fields, a concept resembling today's magneto-hydrodynamic drives used in experimental submarines. What's most haunting isn't just the accuracy of these descriptions, but their context. The Mahabharata recounts aerial battles between Vimanas, complete with weapons that release blazing columns of smoke and fire capable of leveling cities, a passage many compare to nuclear explosions. Another section describes pilots using protective suits and breathing apparatuses, suggesting an understanding of high-altitude physiology millennia before pressurized cabins existed. The question isn't whether ancient India had aerospace engineers in the modern sense. It's why multiple cultures from India's Vimanas to Ezekiel's wheel within a wheel in the Bible described advanced flight technology with such consistent mechanical details. Either these were astonishingly lucky imaginative leaps or fragments of some lost technological epoch filtered through the lens of pre-scientific language. When a Sanskrit text warns that improper Vimana operation could tear the fabric of the atmosphere, it doesn't sound like mythology. It sounds like a cautionary manual from a civilization that understood flight's consequences long before the Wright brothers left the ground. The sea itself seemed to catch fire in the year 673 as an Arab fleet advanced on Constantinople. Byzantine sailors unleashed a weapon so terrifying it defied understanding, a liquid flame that clung to ships and men alike, burning even on water's surface, impossible to extinguish. Known as Greek fire, this 7th century superweapon wasn't just a tool of war. It was a glimpse of modern chemical warfare, a napalm-like substance so advanced its recipe remains lost to this day. Historical accounts describe the horror it inflicted. Flames shot from bronze siphons mounted on Byzantine ships, propelled by pressurized pumps with a range of up to 15 meters. Water only fed the inferno. Sand or vinegar were the sole ways to smother it if crews had time to react before the sticky blaze consumed their rigging and flesh. The psychological impact was as devastating as the physical. Arab chroniclers wrote of sailors leaping into the sea to escape, only to find the fire chasing them across the waves. For centuries, Greek fire guaranteed Byzantine naval dominance, turning the tide of battles that should have been hopeless. What made this ancient flamethrower fuel so potent? The closest modern equivalent is napalm, a mixture of gasoline and thickening agents that adheres to targets while burning at extreme temperatures. Byzantine texts hint at similar chemistry, mentioning ingredients like crude petroleum from the Black Sea, mixed with pine resin for stickiness and quicklime to generate heat upon contact with water. Some theories suggest they added sulfur or saltpeter, creating a primitive form of thermite that could melt through armor. The most compelling clue comes from a 12th century manuscript describing the substance as prepared by art, implying a complex refining process rather than a simple blend of raw materials. The delivery system was equally revolutionary. Byzantine Droman warships housed the flames in sealed, heat-resistant tanks, connected to handheld siphons or fixed turrets via bronze piping. Operators used a force pump, likely based on Heron of Alexandria's designs, to spray the liquid under pressure, an innovation that wouldn't reappear in Europe until the Renaissance. The weapons were so tightly guarded that the secrets of their construction and deployment were reserved for the imperial family alone. When enemies captured siphons, they couldn't replicate the fuel's effects, suggesting Byzantine chemists held knowledge beyond mere mechanical engineering. Modern attempts to recreate Greek fire have yielded mixed results. In 2002, a team from the University of Athens combined light crude oil with pine resin and quicklime, producing a substance that burned on water but lacked the described intensity. Others argue the true formula might have involved distilled naphtha, a technique known to Persian alchemists which would explain its volatility. The missing ingredient could be as simple as human ingenuity. Perhaps Byzantine chemists mastered a stabilization method that prevented premature ignition, a trick lost when Constantinople fell in 1453. What's undeniable is how eerily Greek fire foreshadowed 20th century warfare. The Byzantine siphon operators were the ancestors of flamethrower troops in World War I, their weapons equally feared for the agonizing deaths they inflicted. The substance's water-resistant properties mirror modern firefighting foams designed to combat oil spills, except the Byzantines weaponized the principle centuries earlier. Even the secrecy surrounding its recipe finds parallels in today's classified military research programs. The most haunting lesson of Greek fire isn't about destruction, but about how knowledge rises and vanishes. A technology that defined empires for 800 years disappeared almost overnight when Constantinople fell. Its secrets either burned, buried, or drowned in the Bosporus. It's a pattern we've seen before with the Antikythera Mechanism, with Damascus steel, where brilliance flares bright, then winks out, leaving later generations to puzzle over fragments. Perhaps that's the true power of history's mysteries. They remind us that progress isn't a straight line, but a spiral, where ideas we think are new might just be echoes of forgotten genius. High in the Andes, long before the binary code of zeros and ones shaped our digital age, the Inca wove an entirely different kind of language, one spun not in ink or stone, but in vibrantly dyed chords and intricate knots. These were the quippers, mysterious string devices that some researchers now believe functioned as the ancient world's most sophisticated data storage system. At first glance, they resembled decorative tassels or tangled macrame, but beneath their colorful surface lies a complex coding system that may have recorded everything from tax records to epic poetry, using a logic startlingly close to modern computing. Each quipu consisted of a main chord from which dozens, sometimes hundreds, of pendant strings cascaded like a fibrous waterfall. The devil, or rather the genius, was in the details. Knots varied by type: figure 8, long or coiled, position along the string, and even spin direction. Colors held meaning too, with specific dyes representing categories like crops, livestock, or time periods. Imagine a census document where numbers weren't written but tied, where a red string with 3 figure 8 knots at the 4th position might translate to 3 llamas born in the 4th month. Some quippers even had subsidiary strings branching off main pendants, creating a nested hierarchy akin to folders within digital directories. What's revolutionary is how the system mirrors binary logic. Just as computers encode information through sequences of ons and offs, the quipu's knots and spaces formed a tactile syntax of presence and absence. A knot wasn't just a knot, its position could signify place value, turning strings into a base 10 counting system. The Harvard archaeologist Gary Urton has proposed that the combination of knot direction, chord ply, and color could create over 1,500 unique binary-like combinations, enough to rival early alphanumeric codes. Could these have encoded narratives, not just numbers? Spanish chroniclers wrote that Inca runners carried quippers as letters, suggesting they held linguistic depth beyond mere accounting. The database comparison grows stronger when examining how quippers were used. Provincial administrators sent them to Cusco as bureaucratic reports, with master quipucamayok's keepers of the knots cross-referencing them like ancient spreadsheet analysts. Some quippers show signs of error correction, knots untied and retied, hinting at dynamic data updates. Even more compelling are the narrative quippers described in colonial texts, which supposedly recorded laws and histories. Only a handful of these survive, their stories still locked in fiber. But the real mystery is why this system vanished so completely. After the Spanish conquest, quippers were banned as pagan objects, and the quipucamayok's knowledge died with them. Today, only about 600 quippers remain, most without context. Deciphering them is like trying to reconstruct Excel from a pile of disconnected bar graphs. The structure is visible, but the key is lost. Modern researchers are turning to AI for help, training algorithms to detect patterns across thousands of knot combinations. Early results suggest some quippers may encode calendrical data or even musical notations. The tragedy and the fascination is that we may never fully grasp the quipu's scope. Were some purely numerical, while others held epics as complex as Homer's? did the Inca Empire run on what amounted to a distributed fiber optic network of information, with knots pulsing data across mountain roads instead of electrons through cables? What's certain is that the quipu stands as a testament to human ingenuity's boundless forms. Long before silicon chips, the Inca may have threaded the seeds of information science into strands of wool and cotton, proving once again that progress doesn't follow a single path, it weaves its own. When thick fog swallowed the North Atlantic, Viking ships didn't drift blindly. They navigated by reading sunlight that no human eye could see. At the heart of their secret lay the solarstein, or sunstone, a translucent calcite crystal that could pinpoint the sun's position even through overcast skies or the twilight glow of Arctic summers. Modern experiments reveal these stones worked on principles startlingly close to today's polarized light navigation systems, proving the Norse didn't just conquer rough seas, they hacked the physics of light itself. The magic of the sunstone lies in calcite's unique ability to split light into twin beams through a property called birefringence. By rotating the crystal until these beams matched in brightness, Viking navigators could determine the sun's hidden position with eerie precision. A 2011 study in the Proceedings of the Royal Society put this to the test using a calcite stone under overcast conditions. Even when the sun was completely obscured, the stone's readings aligned with actual solar angles within 5 degrees accuracy, sufficient for crossing thousands of nautical miles. It's no wonder medieval texts describe Norse sailors navigating when neither stars nor moon could be seen. What's astonishing is how closely this mirrors 21st century technology. Modern aircraft and satellites use polarized light sensors for orientation when GPS fails, filtering atmospheric light patterns much like the sunstone did. The Vikings didn't understand the science of polarization, but their empirical mastery of its effects allowed them to build what amounted to a portable weather-proof compass. Archaeologists even uncovered a calcite crystal aboard a 16th century English shipwreck near the Channel Islands, proof the technique outlasted the Viking Age by centuries. But the sunstone was only part of a larger navigational toolkit. Norse sagas mention a sun compass, a wooden disc with a central gnomon that cast shadows corresponding to carved latitude lines. Combined with the sunstone's readings, this created a renewable navigation system needing no iron or magnetism. On the open ocean where cloud cover could last weeks, such tools meant the difference between reaching Greenland's shores and vanishing into the gray. Critics once dismissed sunstones as legend until a pivotal discovery in 2013. Researchers analyzing a 10th century Viking shipwreck in Denmark found calcite crystals aboard, not as cargo but placed near the captain's post, exactly where navigation tools would be stored. Chemical traces proved the stones had been repeatedly handled, their edges worn smooth from use. Suddenly, the myth had material proof. The real brilliance of Viking navigation wasn't just their tools but their systemic redundancy. They tracked wave patterns, bird flights, and even the color of seawater, layering observations like a prehistoric GPS. When fog rolled in, the sunstone offered a backup to the sun compass. When both failed, they relied on bearing dials that recorded wind directions. This multi-layered approach mirrors modern aviation's fail-safes, where pilots cross-check instruments to avoid single-point failures. Why did this technology fade? As magnetic compasses spread from China to Europe, they offered simpler, if less reliable, alternatives. Calcite's fragility meant few sunstones survived, and the oral traditions detailing their use vanished with Norse seafarers. Yet their legacy lingers in unexpected places. Modern polar explorers have resurrected sunstones for expeditions where electronics falter in extreme cold. There's poetic justice in that, a medieval tool outsmarting modern tech in the very environments the Vikings once mastered. What makes the sunstone truly remarkable isn't just its accuracy, but the insight it reveals about ancient minds. The Norse didn't merely endure their environment, they decoded its hidden signals. transforming something as intangible as polarized light into a roadmap across treacherous waters. In an age before laboratories, they conducted 1,000 natural experiments, distilling physics into survival. The next time you check your phone's GPS, remember, the first engineers of light-based navigation didn't wear lab coats. They wore furs, sailed longships, and trusted crystals to guide them through storms we'd still fear today. In the blistering heat of the Persian desert, where summer temperatures could melt stone, ancient engineers built refrigerators that stored ice year-round, without electricity, without compressors, using nothing but wind, water, and sheer ingenuity. These were the Yakchuls, towering mud brick domes that harnessed physics to defy the desert's wrath, creating climates so cold they preserved food and even formed ice during scorching summers. At the heart of this ancient cooling revolution lay wind catchers, ingenious towers that scooped breeze into subterranean chambers, chilling air through evaporation centuries before modern swamp coolers existed. The design was a masterclass in passive thermodynamics. A Yakchul's thick earthen walls, sometimes 2 meters wide, provided insulation against heat, while its tall conical shape allowed hot air to rise and escape through vents at the top. But the real magic happened underground. Networks of qanats hand-dug underground canals channeled water from distant mountains into storage pools beneath the structures. As wind catchers funneled dry desert air over these pools, rapid evaporation dropped temperatures to near freezing levels even in midsummer. The colder air would sink into storage chambers where ice and perishables were kept, creating a natural refrigeration cycle. Some Yakchuls could maintain sub-zero temperatures year-round, with ice formed during winter nights preserved well into the next summer. Modern engineers have measured their effectiveness with awe. A 2018 study in the journal Energy and Buildings recreated a Yakchul's principles in a test structure. Even at 40 degrees Celsius outside, the interior stayed a cool 7 degrees, comparable to a modern refrigerator's crisper drawer. The key was the wind catcher's precise orientation. Persian builders aligned them perpendicular to prevailing winds, ensuring maximum airflow, while internal baffles slowed the breeze just enough to optimize evaporative cooling. It wasn't just architecture, it was meteorology sculpted in clay. What's astonishing is how closely these ancient systems mirror 21st century sustainable design. The wind catcher's function is nearly identical to modern, cool towers used in green buildings today, like Arizona's Biosphere 2, where evaporative pads cool incoming air without energy-intensive compressors. Even the qanat system, which also supplied water for drinking and irrigation, finds echoes in contemporary geothermal cooling, where underground pipes leverage the Earth's stable temperature to regulate buildings above. The Persians essentially built an off-grid, zero-emission HVAC system 2.5 millennia before sustainability became a buzzword. Beyond functionality, the Yakchuls reveal a profound understanding of microclimates. Villages often positioned them near ice farms, shallow basins where water was left to freeze overnight in winter. Workers would harvest the ice at dawn, packing it between insulating layers of straw and sawdust in the Yakchul's depths where it lasted months. This wasn't just cooling, it was an entire cold chain logistics system, enabling everything from chilled sherbets for royalty to preserving medicine for traveling caravans. Historical accounts describe Sasanian kings sending ice as diplomatic gifts to rulers in Mesopotamia, a feat equivalent to shipping glaciers across the desert. The tragedy is how much of this knowledge faded. While some Yakchuls remained in use until the early 20th century, many were abandoned as electric refrigeration spread. Yet their legacy persists in unexpected ways. Iran's contemporary architects are now reviving wind catcher principles in eco-resorts, while Western engineers study them for disaster-resilient cooling solutions in power-scarce regions. The most poetic revival might be in Oman, where modern frost towers inspired by Yakchuls create ice in deserts again. this time to combat water scarcity by harvesting atmospheric moisture. Standing before Yakchal's crumbling dome today, you're not just looking at ancient ruins. You're witnessing a civilization that didn't fight its environment, but danced with it, turning scorching winds into chill vaults and arid emptiness into abundance. In an age of climate crises and energy shortages, these structures whisper an urgent lesson. Sometimes the most advanced solutions aren't invented, they're remembered. Centuries before seismographs could detect the slightest tremor, Chinese scholars were scanning the skies for signs of impending disaster. Ancient records from the Han Dynasty describe earthquakes preceded by eerie atmospheric phenomena, unusual cloud formations, sudden temperature swings, even glowing earthquake lights dancing along the horizon. At the time, these observations were framed through the lens of chi energy imbalances between heaven and earth. But modern science is uncovering a startling truth. Those ancient sky watchers might have been detecting real geophysical signals we now call pre-seismic ionospheric disturbances, electrical anomalies in the upper atmosphere that precede major quakes. The evidence lies in meticulous court records. In 137 BCE, imperial astronomers logged streaks of fire in the night, days before a catastrophic quake leveled part of the capital. A Tang Dynasty text from 817 CE reports yellow dust clouds coiling like snakes, prior to ground ruptures that swallowed villages. What seemed like poetic metaphor now aligns with documented scientific phenomena. Earthquake lights, once dismissed as folklore, have been photographed during modern quakes like the 2009 El Aquila disaster, caused by piezoelectric stress igniting gases along fault lines. As for those twisting dust clouds, researchers from Chapman University found that radon gas released before quakes can ionize air molecules, creating swirling plasma vortices visible under certain conditions. The real breakthrough came when scientists compared ancient Chinese weather logs with contemporary satellite data. In 2008, a team analyzing the 2004 Sumatra earthquake noticed something peculiar. Days before the quake, NASA satellites recorded a dramatic spike in electron density 50 kilometers above the epicenter, exactly the altitude where ancient texts described sky fires. This wasn't coincidence. When tectonic plates grind against each other, the immense pressure generates electromagnetic pulses that travel upward, disturbing the ionosphere much like a stone rippling a pond. The Chinese weren't just observing whether they'd stumbled upon a sophisticated early warning system written in the clouds. Modern attempts to harness these signals are yielding fascinating results. Projects like France's Demeter satellite and China's own earthquake monitoring network now track ionospheric anomalies as potential quake predictors. But the challenge remains distinguishing true precursors from background noise, a problem the ancients tackled through pattern recognition. Imperial meteorologists kept decades of records correlating specific cloud shapes, animal behaviors, and even well water fluctuations with subsequent tremors. Their cloud and rain divination manuals read like proto-scientific field guides, classifying 26 types of pre-seismic cloud formations with uncanny accuracy. Critics argue these connections are retrospective, that humans naturally seek patterns after disasters strike. Yet the consistency across dynasties is hard to ignore. When the same cloud phenomena appear in bamboo records from 200 BCE and again in Ming Dynasty porcelain paintings 1500 years later, it suggests sustained observation rather than myth-making. Most compelling are the preventative measures taken based on these signs: evacuations ordered when ground vapor rose unnaturally, or granaries reinforced after 3 days of red fog. Some scholars estimate these methods may have reduced earthquake deaths by as much as 30% in observant regions. What's haunting isn't just the accuracy of these predictions, but how the knowledge fragmented. While China maintained detailed seismic archives, Europe's medieval scholars dismissed quakes as divine punishment until the 18th century. The irony. Modern geology is now resurrecting ancient Chinese theories through terms like lithosphere-atmosphere-ionosphere coupling, a clunky scientific label for what imperial astronomers once called dragon vapors linking land and sky. The lesson here transcends seismology. It's about re-evaluating how we define observation versus superstition. When a 2,000-year-old text warns that when the mountains breathe fire and the rivers run backward, the earth will soon tremble, we shouldn't dismiss it as primitive poetry. Those words might just be the earliest field notes of a lost science, one that read the sky's subtle shifts like a meteorological Morse code, long before we had instruments to hear its message. One of history's most astonishing artifacts doesn't sit in a lab or a tech museum. It rests quietly in the British Museum's Roman collection, dazzling visitors with a magic trick that defies its 1,600-year age. The Lycurgus cup, a 4th century chalice carved from dichroic glass, shifts color like a chameleon depending on the light. Hold it under sunlight and it glows a translucent jade green. Shine a light from within and the entire vessel transforms into a deep blood red. This isn't just artistic flair, it's nanotechnology crafted by Roman artisans who embedded gold and silver particles so small they manipulate light at the molecular level. Modern electron microscopy reveals the cup's secret. Its glass contains a precise mixture of gold and silver nanoparticles, each roughly 70 nanometers across, about 1,000 times smaller than a human hair's width. These particles scatter light in a process called plasmon resonance, absorbing and reflecting specific wavelengths to create the color-changing effect. The precision is mind-boggling. Too much gold and the red would vanish, too little silver and the green would dull. Roman craftsmen achieved this balance without microscopes or spectrometers, likely through a technique called colloidal staining, dissolving tiny amounts of precious metals into molten glass and cooling it under exacting conditions. The result, a material so advanced, similar photonic crystals are now used in cutting-edge fiber optics and biosensors. The eerie part, we still don't fully understand how they did it. Replicating the cup's properties took 21st century scientists years of trial and error. In 2013, researchers at the University of Illinois finally cracked the code, confirming the nanoparticles were intentionally added, not accidental impurities. The Romans might not have grasped the quantum physics behind their creation, but their empirical mastery of materials was so refined, they essentially engineered light itself. What's even more striking is how this ancient tech mirrors modern applications. Today, dichroic glass adorns everything from spacecraft visors to high-security holograms, manipulating light for practical and aesthetic purposes. Gold nanoparticles are used in medical diagnostics to detect pathogens, while photonic crystals enable high-speed data transmission through fiber optic cables. The Lycurgus cup wasn't just ahead of its time, it was a blueprint for technologies we've only begun to explore. Why isn't this technique more common in ancient artifacts? The answer might lie in the cost and rarity of the materials. The cup's survival suggests it was a treasured imperial possession, possibly a ceremonial vessel for elite rituals. Other examples, like fragments found in Byzantine mosaics, hint at a secretive tradition passed down through select workshops. When Rome fell, the knowledge may have vanished with them, leaving the cup as a lone relic of a lost nanoscience. Yet here's the twist: the Lycurgus effect isn't the only example of Roman nanoengineering. Recent studies of 1st century glassware from Pompeii revealed similar nanoparticles, suggesting the technology was more widespread than we thought. Some scholars now believe the famous Portland vase, another Roman masterpiece, might owe its cameo-like layers to controlled metal infusion. It's a humbling realization. While we credit modern labs with nanotech breakthroughs, ancient artisans were manipulating matter at the same scale, armed only with fire, intuition, and centuries of observational genius. The cup's final mystery isn't technical but philosophical. Why invest such effort into a drinking vessel the answer might lie in its depiction of King Lycurgus ensnared by vines, a moral tale about the dangers of excess. As light passed through the cup, the scene would literally transform, reinforcing its message with physics as much as imagery. This wasn't just decoration, it was storytelling engineered at the atomic level, a fusion of art and science so seamless it still feels futuristic. Standing before the Lycurgus cup today, you're not just looking at an ancient relic, you're seeing a window into a world where craftsmanship and cutting-edge science were one and the same, a reminder that the boundaries of human ingenuity have always been far wider than we assume. The Romans didn't just make glass, they tamed light itself, leaving behind a shimmering puzzle that still challenges what we know about the past and what might yet be possible in the future. For 40,000 years, long before satellites or sextants, Aboriginal Australians traversed a continent twice the size of Europe without maps because the land itself was written into song. These weren't mere melodies but living geodatabases encoded with startling precision. Known as songlines, these intricate oral maps wove topography, navigation, and lore into rhythmic verses so accurate that modern studies show they can guide a traveler to within meters of a waterhole, mountain, or sacred site across hundreds of kilometers. Imagine a GPS that doesn't need batteries, just memory, passed down through generations in a chain of knowledge unbroken since the Ice Age. The mechanics of songlines reveal a staggering fusion of art and science. Each verse corresponds to specific landmarks. A rock formation might be sung as a particular note, a river bend as a rhythmic pause. The contours of the melody mirror the landscape's rise and fall, with tempo shifts indicating changes in terrain. A slow, heavy rhythm could signal trudging through sand dunes, while quickening beats might mark the approach to a valley. Even the lyrics' phonetics hold meaning. Certain syllables mimic animal calls or wind patterns unique to locations, acting as acoustic signposts. When anthropologists from the University of Melbourne mapped songlines against satellite imagery, they found the correlation wasn't just approximate, it was cartographically precise, with sung coordinates aligning to within 50 meters of actual GPS readings across routes spanning the entire continent. What's revolutionary is how these songs function as four-dimensional maps. While Western cartography flattens geography onto paper, songlines encode time as fluidly as space. The same verse might describe a creek's summer drying pattern or the seasonal movement of kangaroo herds, layering ecological calendars over spatial waypoints. Some songlines even account for celestial shifts, adjusting routes based on the position of the Southern Cross during different lunar cycles. This temporal adaptability puts modern digital mapping to shame. Google Maps can't tell you when monsoon rains will transform a desert wash into a raging river, but a well-preserved songline can. The real genius lies in the system's redundancy. Unlike a physical map lost to fire or flood, songlines were safeguarded through communal ownership. Multiple clans knew segments of the same route, ensuring survival even if one group dispersed. Initiates learned songs through a rigorous process of walking and singing the land simultaneously, imprinting muscle memory alongside melody. Errors were self-correcting. If a singer deviated from the true path, the rhythm would clash dissonantly with the actual terrain, signaling a mistake. This built-in verification mirrors modern blockchain's distributed ledger concept, where consensus prevents data corruption. Modern expeditions have put songlines to the test with jaw-dropping results. In 2017, a group of non-indigenous rangers attempting to locate remote water sources in the Tanami Desert, an area larger than Greece, relied on Warlpiri songlines shared by elders. Despite having no prior experience in the region, they located 5 undocumented springs within a 15-kilometer radius using only the sung directions. Similarly, during Australia's devastating 2019 bushfires, Noongar songlines helped emergency crews find ancient underground aquifers when modern hydrographic charts failed. Yet these living maps face existential threats. Climate change is altering landscapes faster than songs can adapt, with sacred sites swallowed by rising seas or erased by droughts. Mining projects carve through songline routes, severing the connection between verse and geography. Linguists estimate that of the 250 original Aboriginal languages, only 13 remain strong enough to sustain the full complexity of songline transmission. Efforts are underway to preserve them. Digital databases now archive thousands of hours of songline recordings, while universities collaborate with elders to transcribe routes with augmented reality overlays. But the true magic of songlines lies in their orality, in the way breath and soil intertwine during live performance. The deeper wonder isn't just their navigational brilliance, but what they reveal about human cognition. Neuroscientists studying Aboriginal spatial memory found their hippocampus, the brain's mapping center, is significantly more developed than average. Songlines don't just describe the land, they sculpt the mind itself, turning gray matter into living atlas. In an age where we blindly follow turn-by-turn phone alerts, these ancient melodies whisper a radical alternative. That true navigation isn't about passive instruction, but about weaving yourself into the story of the earth. Every note a longitude, every pause a latitude, and the whole world humming back in reply. 4,000 years before calculators, Babylonian scribes etched equations into wet clay that could predict planetary motion, calculate compound interest, and even optimize crop yields, all using a numerical language so advanced modern computers still borrow its logic. These weren't crude tallies, but sophisticated algebraic tablets solving quadratic equations with methods textbooks would later credit to Renaissance mathematicians. The most astonishing part, they did it all in base 60, a number system so versatile it still governs how we track time and navigate the stars today. Take tablet YBC 7289, unearthed in the ruins of a scribble school. At first glance, it's just a square with diagonal lines, but the cuneiform numbers reveal something extraordinary, an approximation of the square root of 2 accurate to 6 decimal places, calculated 1700 years before Pythagoras was born. The Babylonians didn't just stumble upon this value, they derived it through iterative algorithms resembling modern numerical analysis. Another tablet, Plimpton 322, contains 15 perfect Pythagorean triplets, suggesting they understood right-angle trigonometry over a millennium before the Greeks formalized it. Their real genius lay in abstraction. While Egyptian math focused on practical measurements, Babylonian tablets like MLC 1950 show purely theoretical problems, wordless equations solving for unknowns they called the thing. This shift from concrete to abstract thinking mirrors the leap from arithmetic to algebra, complete with symbolic placeholders that functioned like early variables. A tablet from Susa even details a step-by-step solution for a cubic equation, a feat European mathematicians wouldn't replicate until the 16th century. The base 60 system, often dismissed as cumbersome, was their secret weapon. Unlike our base 10, 60 has 12 divisors, allowing cleaner fractions critical for astronomy and engineering. Traces remain everywhere, 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle, all Babylonian inheritances, but their computational brilliance went deeper. Tablets like VT 785 demonstrate reciprocal tables used to convert division into multiplication, a technique modern processors employ to speed up calculations. They essentially invented lookup tables, a cornerstone of computer science millennia before silicon chips existed. What's haunting is how closely their methods resemble programming logic. A tablet now housed at Yale describes an algorithm for calculating compound interest that reads like pseudocode. Take the principal, multiply by the rate, add to the original sum, repeat for each year. Another outlines a trapezoidal land survey method identical to numerical integration techniques rediscovered in calculus. Even their astronomical tablets, like the Venus tablet of Amasajuka, used repeating sequences and error corrections akin to today's iterative machine learning models. The tragedy isn't that this knowledge vanished, it's that we forgot its origins. Greek mathematicians like Hipparchus openly credited Babylon for their star charts, yet later European scholars assumed algebra sprang fully formed from the Arab world. Only in the 19th century, when archaeologists deciphered cuneiform math tablets, did we realize the depth of this ancient numerical revolution. Perhaps the ultimate testament to their legacy lies in the sky. Next time you check the time or glance at GPS coordinates, you're navigating via a 4,000-year-old framework, proof that some ideas are so perfectly engineered, they outlast empires, languages, and even the clay they were written on. The Babylonians didn't just do math, they built the invisible scaffolding of modern computation, one wedge-shaped stroke at a time. Imagine losing your nose as punishment for adultery, only to have it rebuilt with skin from your cheek, a procedure so advanced it wouldn't be matched in Europe for over 2,000 years. This wasn't science fiction but routine surgery in ancient India, where the physician Sushruta documented intricate plastic surgery techniques in his 6th century BC medical compendium, the Sushruta Samhita. Far from primitive trial and error, these texts describe reconstructive procedures with a precision that would make modern surgeons pause, including the world's first recorded rhinoplasty, cheek flap grafts, and even earlobe repairs, all performed without anesthesia, antibiotics, or sterile instruments. The details are shockingly modern. Sushruta's nose reconstruction method, used to restore features amputated as punishment or lost in battle, followed steps still echoed in today's operating rooms. First, a leaf template was cut to match the missing nose's dimensions. Then, a flap of living skin was carefully sliced from the patient's forehead or cheek, left partially attached to maintain blood flow, a technique now called a pedicle graft. The flap was twisted into position, shaped with sutures made from horsehair or ant heads, and nostrils were recreated using reed tubes to prevent collapse during healing. The text even advises post-operative care, applying herbal pastes to reduce swelling and avoiding foods that might disrupt recovery. What's revolutionary isn't just the technical skill, but the underlying understanding of anatomy and physiology. Sushruta described over 300 surgical instruments, including scalpels with curved tips for precise incisions and forceps resembling modern hemostats. His chapters on wound healing reveal knowledge of microbial contamination centuries before germ theory, advocating boiling instruments and using antiseptic turmeric and honey poultices. The Samhita even details nerve repair techniques, advising surgeons to reconnect severed ends, like joining two lotus fibers, a poetic analogy masking what we now recognize as early peripheral nerve surgery. Modern medicine has validated much of this ancient wisdom. In 2008, surgeons at London's Royal College studied Sushruta's methods and found his cheek flap rhinoplasty produced results nearly identical to contemporary techniques, with comparable vascularization and minimal scarring. His descriptions of skin graft viability align with modern understanding of angiogenesis, where new blood vessels form to nourish transplanted tissue. Even his insistence on practicing incisions on gourds and fruit before operating on humans mirrors today's surgical simulations. Yet the most startling revelation lies in the Samhita's philosophical framework. Sushruta didn't view surgery as mechanical repair but as a sacred act of restoring dignity. His text opens with a profound declaration: "The physician who approaches the patient like a father with compassion and devotion succeeds best." This ethos, prioritizing both technical excellence and emotional care, foreshadows modern holistic medicine by millennia. When Western surgeons discovered Indian techniques in the 18th century through British colonial reports, they were stunned by their sophistication. Joseph Constantine Carpew spent 20 years studying Sushruta's methods before performing Europe's first documented rhinoplasty in 1815, a procedure still called the Indian method in medical literature. Why did this knowledge remain hidden for centuries? Partly due to cultural fractures, Sushruta's texts were preserved in Sanskrit, while Europe's medical tradition stemmed from Greek and Arabic sources. But also because we underestimate ancient innovation. The Samhita wasn't just ahead of its time, it anticipated entire branches of medicine, from dermatology to anesthesiology. It even describes using cannabis vapor for pain relief. Today, as regenerative medicine explores growing replacement tissues from stem cells, we're circling back to Sushruta's core insight: the body's innate capacity to heal when guided by skilled hands and unwavering compassion. The next time you see a news story about 3D printed organs or robotic surgery, remember the foundations weren't laid in Silicon Valley labs, but on the banks of the Ganges over 2.5 millennia ago, where a surgeon-philosopher codified principles we're still striving to perfect. In the delicate art of rebuilding faces and lives, Sushruta's legacy proves that true innovation isn't just about discovering new things, but remembering old wisdom we've forgotten. Long before the whirring of microservos and the glow of LED eyes, ancient Greece dreamed of robots not as cold machines, but as enchanted servants brought to life by gears and hydraulics. The engineer Philo of Byzantium, working in the 3rd century BC, described automata so lifelike they could pour wine, play music, and even refill guests' cups without human intervention. These weren't mythical fantasies. Archaeologists have uncovered remnants of these mechanical marvels, revealing a level of engineering sophistication that eerily prefigures modern robotics. One of Philo's most famous designs was the automatic servant, a life-sized figure that held a jug of wine in its hands. When a cup was placed in its palm, a series of counterweights and levers triggered the pouring mechanism, stopping precisely when the cup was full, an ancient analog to today's liquid dispensing robots. The secret lay in its airtight vessel design. As wine flowed out, air pressure inside the jug decreased, creating suction that eventually halted the stream. This same principle powers modern barista robots that craft perfect espresso shots, balancing flow rates and pressure with uncanny similarity to Philo's 2,000-year-old prototype. But the Greeks didn't stop at wine pourers. Philo's writings describe entire scenes of automation, mechanical birds that sang when a temple door opened, hydraulic statues that raised their arms in blessing, even a robotic theater where miniature ships sailed across a stage powered by hidden water wheels. The most sophisticated of these devices, the moving Pegasus, used a system of steam valves to flap wings and take flight along a track, a direct ancestor to the animatronics that bring theme park characters to life today. What's unsettling is how closely these ancient automata mirror modern robotics concepts. Philo's inventions relied on feedback loops, mechanisms that adjusted their behavior based on external inputs, much like the sensors guiding today's robotic vacuum cleaners. His wine pourer, for instance, didn't just dump liquid indiscriminately. It responded to the weight of the cup, a primitive form of haptic feedback. Similarly, his singing birds used wind pressure to modulate pitch, creating an early example of programmable sound generation. Critics once dismissed these accounts as exaggerated until reconstructions proved otherwise. In 2014, a team from the University of Crete built a functional replica of Philo's automatic servant using period-accurate materials. The result wasn't just a curiosity, it performed with startling reliability, its bronze mechanisms operating smoothly without electricity or modern lubricants. The team noted how Philo's designs incorporated fail-safes we still use, like tapered valves to prevent leaks and weighted governors to control speed. The cultural context makes these inventions even more extraordinary. Greek automata weren't hidden in workshops, they were displayed in temples and wealthy homes, blending engineering with artistry. Some scholars argue they embodied the Greek concept of thauma, or wondrous spectacle meant to bridge the gap between human ingenuity and divine power. When a mechanical Heracles labored on a miniature stage or a bronze eagle turned its head to follow the sun, audiences didn't just see gadgets, they witnessed magic made tangible. Why didn't this spark an industrial revolution? The same constraints that limited Heron's steam engine applied here. These were prestige projects, not scalable technologies. Without precision, metal casting or mass production, automata remained one-off luxuries, yet their influence persisted. Byzantine emperors later commissioned golden mechanical lions that roared at court, and medieval Arab scholars like Al-Jazari expanded on Philo's principles with elephant clocks and automated musicians. The eerie truth is that Philo's inventions represent a road not taken, one where mechanical automation flourished centuries before the microchip. When you watch a modern robot arm assemble a car or a drone deliver a package, you're not just seeing the future. You're seeing the resurrection of a 2,000-year-old dream, where gears and levers first whispered the promise of artificial hands that never tire. The Greeks may not have had silicon or software, but they understood robotics' most profound lesson. The line between tool and servant is thinner than we think. The jungles of Mesoamerica held a secret so valuable, so advanced, that when Spanish conquistadors first encountered it, they assumed it was witchcraft, a stretchy, bouncy substance unlike anything in Europe. The Olmec civilization, thriving over 3,000 years ago, didn't just harvest rubber from local trees. They engineered it through a chemical process so precise, it wouldn't be replicated until Charles Goodyear patented vulcanization in 1844. But the Olmec weren't making tires or industrial hoses. Their genius was poured into something far more unexpected. The world's first high-performance sports equipment, massive rubber balls used in a ritual game that echoed through their sacred cities. At the heart of this innovation was the humble sapodilla tree, whose milky latex could be transformed from a sticky liquid into a durable, elastic solid. The Olmec discovered that mixing this latex with morning glory vine juice, a plant containing sulfur-like compounds, created a chemical reaction when heated. Archaeologists at El Manotti, a swampy Olmec sacrificial site, unearthed rubber balls dating back to 1600 BC that retained their bounce after millennia underwater. Modern spectroscopy revealed why. The vine's organic acids had cross-linked the latex's polymer chains, just as sulfur does in modern vulcanization. The Olmec didn't stumble upon this formula. They perfected it through generations of experimentation, adjusting ratios and curing times to achieve specific performance characteristics. The scale of production still stuns researchers. At the Olmec capital of La Venta, remnants of rubber workshops suggest standardized manufacturing, with balls ranging from handheld sizes to monstrous spheres nearly a meter in diameter, weighing up to 4 kilograms. These weren't simple playthings, they were engineered for the brutal, fast-paced ball game that dominated Mesoamerican culture. Wall carvings depict players wearing padded belts, striking the ball with hips and thighs in matches that could last hours. The physics were astonishing. A well-struck rubber ball could reach speeds over 70 kilometers per hour, ricocheting off stone courts with enough force to fracture bones. The Olmec optimized their rubber's rebound, creating formulations that balanced elasticity with durability. Some balls could bounce over 3 meters high after being dropped from shoulder height. But the brilliance didn't stop at sports. Excavations at Olmec port cities like Canton Corralito uncovered rubber-coated fabrics, proof they waterproofed capes and footwear centuries before Macintosh's 19th-century raincoats. Chemical analysis shows they tailored rubber's properties for different uses: stickier blends for adhesive sealants, more rigid versions for tool handles, even flexible sheets that may have been early attempts at inflatable devices. The Aztecs later called this material ollie, giving us the word rubber, but the Olmec were its true pioneers. What's tragic is how close this knowledge came to vanishing. Spanish chroniclers, horrified by the ball game's ritual associations with human sacrifice, destroyed countless rubber artifacts. Only in the 1990s, when researchers compared ancient rubber's molecular structure to modern samples, did the Olmec's scientific achievement come to light. Today, their legacy lives on in unlikely places, from the vulcanized soles of your sneakers to the bouncy balls in arcade machines. The next time you marvel at a rubberized gadget, remember, the first polymer engineers didn't wear lab coats. They wore jaguar pelts played under the Mesoamerican sun and turned tree sap into a technology that still shapes our world, 3 millennia before the rest of humanity caught up. Hidden among the medical papyri of ancient Egypt lies a fertility test so eerily accurate that modern scientists were stunned to confirm its effectiveness. The Berlin Papyrus, dating back to 1350 BC, describes a method where women urinated on bags of barley and wheat. If the grains sprouted, pregnancy was confirmed. At first glance, it sounds like pure superstition. But when researchers at the National Institute of Health actually tested this 3,000-year-old technique in 1963, they found something remarkable. The test correctly identified pregnancy with approximately 70% accuracy, outperforming some 20th-century methods. The secret lies in the biochemical sensitivity of these ancient grains. Modern science reveals that pregnant women's urine contains elevated levels of estrogen, a hormone that stimulates seed germination. Wheat and barley respond dramatically to these hormonal cues, with studies showing they sprout faster and more vigorously when exposed to urine from pregnant individuals. The Berlin Papyrus even specifies that if barley sprouted first, the child would be male; if wheat sprouted faster, female. While the gender prediction lacks scientific basis, the core diagnostic principle holds up. Urine-based pregnancy tests wouldn't reappear until the 1920s, when German scientists developed the Aschheim-Zondek test using mice, a method far more cumbersome than the Egyptians' elegant grain solution. What's even more astonishing is the diagnostic sophistication embedded in these instructions. The Ebers Papyrus, another medical scroll, advises performing the test over multiple days and comparing sprout growth rates, essentially creating an early quantitative assay. Some passages even recommend testing at specific times of day, aligning with modern knowledge that hormone concentrations fluctuate. This wasn't blind trial and error, it was careful clinical observation codified into repeatable methodology. Critics argue the test's reliability varies based on grain variety and urine composition, but the underlying principle remains sound. Contemporary research into plant bioassays shows certain seeds can detect human chorionic gonadotropin (HCG), the same hormone modern stick tests identify, at concentrations as low as 5 international units per liter. The Egyptians, of course, knew nothing about HCG. Yet through generations of observation, they recognized that pregnancy produced consistent, measurable changes in biological materials, the very foundation of modern diagnostics. Perhaps most striking is how this ancient knowledge persisted across cultures. Greek physician Hippocrates described a similar test using watered wine and honey, while medieval European piss prophets claimed to diagnose pregnancy from urine's color and clarity. But the Egyptian method stands out for its empirical precision. They didn't just look for mystical signs, but recorded germination rates, documented control comparisons, and even accounted for seasonal variables affecting grain viability. Today, as scientists explore plant-based biosensors for everything from environmental toxins to cancer markers, we're circling back to principles the Egyptians grasped millennia ago. That humble jar of barley wasn't just a pregnancy test, it was a pioneering example of bioresponsive technology, proving once again that some of history's most advanced ideas don't come packaged in microchips, but in the quiet wisdom of seeds and soil. 2,000 years before fracking transformed the global energy landscape, Chinese engineers were already mastering the art of harvesting natural gas, not for heating homes or fueling factories, but for something far more unexpected: seasoning their food. Deep in the salt mines of Sichuan during the Han Dynasty, workers stumbled upon pockets of fire wells where escaping gas could be ignited into towering flames. Instead of fleeing these dangerous seepages, they saw opportunity. By the 1st century BC, bamboo pipelines snaked across the province, delivering natural gas to boiling houses where it fueled vast iron pans of evaporating brine, creating what may have been history's first large-scale chemical industry powered by fossil fuels. The engineering behind this ancient gas network was astonishingly sophisticated. Workers drilled boreholes up to 600 meters deep using derricks made of bamboo and wood, with iron bits pounding relentlessly into the earth. When they struck gas, they capped the wells with bamboo and mud valves, then connected them to distribution lines crafted from hollowed-out bamboo trunks. These pipes weren't simply laid on the ground, they were sealed with lacquer and wrapped in hemp to prevent leaks, forming pressurized systems that could transport gas several kilometers to salt evaporation sites. Modern analysis of residue inside excavated bamboo pipes confirms they carried methane concentrations high enough to sustain continuous combustion, proving these weren't occasional natural seeps but carefully managed fuel supplies. What's even more impressive is how they managed the dangers. Han Dynasty texts describe using leather bellows to test for gas leaks before lighting flames, and positioning boiling pans on elevated platforms to control heat intensity, early precursors to modern pressure regulation systems. At the heart of the operation were the fire masters, specialists who adjusted bamboo valves to balance gas flow, much like today's pipeline technicians monitor control stations. Excavations at ancient salt works reveal carbonized remnants of gas nozzles where flames roared under iron pans 24 hours a day, evaporating brine into precious salt crystals. The scale of this industry rewrites our understanding of ancient energy use. At its peak during the Tang Dynasty, Sichuan's brine boilers consumed an estimated 700 million cubic meters of natural gas annually, comparable to the energy needs of a small modern city. Archaeological surveys have mapped over 200 ancient drilling sites clustered around Zigong, where some wells remained productive for centuries. Unlike modern wells that exhaust quickly, Han engineers practiced sustainable extraction, deliberately limiting flow rates to preserve reservoirs. Their bamboo pipelines formed networks stretching hundreds of kilometers, rivaling early 19th century gas systems in London and Baltimore. Why didn't this spark an industrial revolution? The answer lies in the salt itself. For the Chinese, gas was merely a means to produce their most strategic commodity, salt, for preserving food and paying imperial taxes. There was no incentive to adapt the technology for other uses when bamboo pipelines served their narrow purpose perfectly, but the legacy of these early drillers lives on. When Western oil companies arrived in Sichuan in the 19th century, they were shocked to find locals still using Han-era techniques to extract gas, complete with BOO Chinese letter tools and hand-operated drill bits. Today, the Zigong Salt History Museum preserves a functioning replica of an ancient gas well, its bamboo pipes hissing with the same flammable bounty that once fueled an empire's kitchens, proof that the energy age didn't begin with coal or steam, but with hollow bamboo and the relentless pursuit of perfect seasoning. Buried beneath the ash of Mount Vesuvius, a treasure trove of medical instruments lay preserved for nearly 2,000 years, not as primitive relics, but as gleaming examples of surgical precision that would feel startlingly familiar in any modern operating room. Among the ruins of Pompeii's House of the Surgeon, archaeologists uncovered a collection of bronze and iron tools so advanced that their designs remain virtually unchanged today. From razor-sharp scalpels with interchangeable blades to finely calibrated bone drills and artery clamps, these artifacts reveal a level of medical sophistication that challenges our assumptions about ancient medicine. Take the Roman scalpels, for instance, crafted from steel with detachable handles. They feature narrow, double-edged blades designed for making precise incisions nearly identical to today's #10 and #15 surgical blades used for everything from appendectomies to cosmetic surgery. Some even had sleek, ergonomic grips to reduce hand fatigue during lengthy procedures, a detail modern manufacturers only standardized in the 20th century. The most astonishing find, a set of cataract needles so delicately tapered that ophthalmologists examining them confirmed they could still be used for eye surgery with minimal modification. But the parallels don't stop at cutting tools. Roman forceps excavated from Pompeii's baths and hospitals include designs like the molar tooth variety for extracting teeth and the mosquito style for clamping blood vessels, both terms still used in surgical supply catalogs today. One particularly sophisticated specimen, a vaginal speculum, features a screw mechanism to gently dilate tissue, mirroring the adjustable designs found in contemporary gynecology clinics. Even their bone drills, with modular bits and rounded guards to prevent overpenetration, resemble modern orthopedic equipment used in spinal surgeries. What's truly remarkable is how these tools reflect an understanding of sterilization long before germ theory existed. Many Pompeian instruments were found stored in sealed bronze cases, while others showed signs of being heated before use, a crude but effective form of infection control. Writings from Galen, the famed Roman physician, describe boiling instruments in vinegar or exposing them to open flames between procedures, practices that foreshadowed 19th century antiseptic techniques pioneered by Joseph Lister. Some scalpels even had small notches near the base, possibly for tying antiseptic-soaked linen during wound closures. Critics once dismissed these tools as rare luxuries, but recent discoveries prove otherwise. Excavations across the empire, from military hospitals along the Rhine to civilian clinics in Roman Britain, have uncovered nearly identical instrument sets, suggesting standardized mass production. X-ray fluorescence studies reveal consistent metal alloys, while where patterns indicate repeated sharpening and reuse, much like modern hospitals' instrument maintenance protocols. The most haunting question isn't how they made these tools, but why their knowledge vanished. After Rome's fall, European surgical practices regressed for centuries, with Dark Age physicians often resorting to crude amputation saws. Only during the Renaissance did surgeons rediscover techniques the Romans had mastered, like using hollow needles to drain abscesses or specialized hooks to remove nasal polyps. Perhaps the ultimate testament to their ingenuity lies in the scalpel's enduring form, a tool so perfectly designed 2 millennia ago that even today's space-age materials haven't improved its basic function. Standing in the shadow of Vesuvius, it's hard not to wonder, if this was the equipment left behind in a provincial town's workshop, what marvels might have been wielded in Rome's finest operating theaters. The past keeps surprising us, not with alien oddities, but with the uncanny familiarity of brilliance that transcended time. Long before Bitcoin miners raced to solve cryptographic puzzles, the Maya were running what might have been history's first blockchain, except their ledger wasn't digital but edible. In the bustling markets of Tikal and Calakmul, shoppers didn't carry coins or paper bills. They traded in cacao beans, a currency so deeply embedded in Mesoamerican economics that Spanish conquistadors reported thieves counterfeiting them by carving empty bean husks and filling them with mud. This wasn't just barter. It was a sophisticated monetary system with eerie parallels to modern cryptocurrency, from decentralized validation to built-in inflation controls. The genius of Mayan chocolate money lay in its self-regulating design. Unlike gold or silver, cacao beans couldn't be arbitrarily mined. They grew in specific climates, requiring exacting horticultural knowledge. The Maya cultivated cacao in carefully managed orchards, controlling supply much like central banks adjust currency circulation today. But here's where it gets fascinating. The beans' value wasn't dictated by royal decree. Their worth emerged organically through collective agreement, a decentralized trust system mirroring crypto's consensus protocols. When a merchant accepted 10 beans for a turkey or 20 for a jade ornament, they weren't following government-set exchange rates. They were participating in a network-wide valuation system where market forces and cultural consensus determined purchasing power, the same principles underlying Bitcoin's peer-to-peer valuation. Archaeological evidence reveals just how advanced this system became. Excavated Maya sites contain standardized banking vessels for storing beans, some holding exactly 8,000, a possible precursor to bulk denominations like modern bankrolls. Glyphs describe interest-bearing cacao loans, with repayment schedules tracked using calendar wheels that functioned like primitive smart contracts. Even anti-counterfeiting measures were remarkably sophisticated. Beans were often traded still encased in their aromatic pods, allowing verification through smell and taste, a biological authentication system far harder to spoof than watermarks on paper bills. The most striking parallel comes from the Maya's solution to inflation. As cacao production expanded, they didn't experience the currency devaluation that plagues modern economies. Why? Because they literally consumed their money. Cacao wasn't just wealth, it was a coveted food and ritual beverage constantly being removed from circulation through daily use. This created natural deflationary pressure, keeping the system stable without central oversight. Compare that to Bitcoin's built-in scarcity. Only 21 million will ever exist, or Ethereum's burn mechanisms that destroy tokens to maintain value. The Maya accidentally engineered a self-correcting monetary ecology 3,000 years before Wall Street quant traders discovered velocity of money. Modern crypto enthusiasts might scoff at comparing blockchain to beans, but the underlying psychology is identical. Both systems rely on collective faith in an object's worth rather than intrinsic value. After all, a cacao bean has no more practical utility than a Bitcoin's hash code. The Spanish initially dismissed Maya money as primitive, only to later adopt it themselves when they realized its stability. The same pattern repeats today as traditional banks initially mocked cryptocurrency, only to now race toward adopting its decentralized principles. What the Maya understood, and what modern finance often forgets, is that money works best when it's tied to something tangible yet flexible. Their cacao economy collapsed not because of flaws in the system, but because Spanish colonizers flooded markets with beans plundered from new territories, destroying the careful supply balance. It's a cautionary tale for crypto's current growing pains. Decentralization thrives on equilibrium, not exploitation. When Cortés' soldiers pocketed their first chocolate coins, they weren't just stealing wealth. They were unraveling an economic philosophy we're still struggling to reinvent. Perhaps the ultimate irony, today's artisanal chocolate makers spend fortunes sourcing heirloom cacao varieties, the same beans their ancestors once used to buy kingdoms. The circle of value remains unbroken, just awaiting the next civilization to rediscover its bitter-sweet potential. From the gears of the Antikythera Mechanism predicting celestial movements to the self-healing Roman concrete that still stands strong today, these 25 ancient predictions reveal minds that weren't just ahead of their time. They seem to have glimpsed fragments of our modern world long before science caught up. Was it coincidence, divine inspiration, or something even more extraordinary, proof of civilizations so advanced their knowledge was lost to the ages, surviving only as myths and scattered artifacts? Consider the sheer breadth of these innovations. The Maya tracked eclipses with mathematical precision while medieval Europe still feared them as omens. The Norse navigated treacherous seas using polarized light centuries before physicists understood its properties. Sushruta performed intricate surgeries in ancient India that wouldn't be replicated in the West for millennia. These weren't lucky guesses, they were systematic, repeatable achievements, each one a puzzle piece suggesting a larger, forgotten picture. What's most haunting isn't the individual discoveries, but the patterns connecting them. Cultures separated by oceans and centuries, from the Baghdad Batteries to the Olmec rubber vulcanization, arrived at shockingly similar solutions. The Greeks dreamed of robots, while the Vedic text described aircraft with eerie technical detail. The Chinese tracked seismic precursors in the ionosphere, while Roman engineers nano-engineered glass. If these ideas emerged in isolation, why do they align so perfectly with technologies we consider modern breakthroughs? Perhaps the line between myth and science was never as clear as we thought. The magic described in ancient texts often reads like garbled accounts of advanced technology: Greek fire as napalm, the Dendera carvings as electrical diagrams, the Vimanas as spacecraft. Even Plato's tale of Atlantis, long dismissed as allegory, now sparks serious geological debates about Bronze Age superfloods and lost cities beneath the waves. So where does this leave us? Three possibilities whisper through these artifacts. Maybe humanity's ingenuity has always cycled between peaks and valleys, with dark ages erasing progress again and again. Perhaps some cultures glimpsed universal scientific truths through sheer observation, their insights buried under time's rubble. Or just maybe there's another story, one we're only beginning to decipher from these fragments. Now it's your turn. Which of these ancient predictions left you awestruck? Was it Zhang Heng's earthquake detector, so precise it rivals modern seismographs? The Incas' knotted quippers that may have encoded entire epics? Or the Viking sunstone that turned sunlight into a compass? Drop your favorite in the comments, and if you're hungry for more mysteries where history blurs into science fiction, hit subscribe. The past isn't done surprising us yet. Somewhere out there, another artifact waits, ready to rewrite what we thought we